Space is vast. It's filled with wonders. Among them, black holes stand out. They are objects of immense power, shrouded in mystery. Imagine a place where gravity is king, so strong that nothing, not even light, can escape. This is a black hole. Black holes challenge our understanding of the universe. They push the boundaries of physics. These celestial objects are a testament to the universe's power and our own thirst for knowledge. They beckon us to explore, to unravel their secrets. Their existence, once a mathematical curiosity, is now confirmed. Through telescopes, we've observed their influence. We've detected their gravitational pull. Black holes are not just theoretical constructs, they are real. These cosmic enigmas spark our curiosity. They ignite our imaginations. Join me as we journey into the heart of these celestial wonders. Let's explore the science and the mystery of black holes. Stars, the building blocks of galaxies, have life cycles. These cycles are as varied and complex as the stars themselves, spanning millions to billions of years. They are born in vast clouds of gas and dust known as nebulae. Over time, gravity pulls these particles together, forming a protostar. As the protostar continues to gather mass, its core heats up, eventually igniting nuclear fusion. They shine brightly for millions or even billions of years, but like all things, they eventually die. The death of a star can be a spectacular event, often marked by a supernova explosion, which can outshine entire galaxies for a brief period. This explosive death can lead to the creation of some of the universe's most extreme objects, transforming the remnants of the star into something entirely new and fascinating. Black holes, for instance, are born from the remnants of massive stars, stars much larger than our own sun. These colossal stars, often tens of times the mass of the sun, live fast and die young in cosmic terms. When these massive stars exhaust their nuclear fuel, they can no longer support themselves against the force of gravity. They collapse under their own weight in a catastrophic event that compresses their core to unimaginable densities. This collapse crushes the star's core, causing it to shrink dramatically. The core's density increases exponentially as it is compressed into a smaller and smaller volume. If the core is massive enough, the collapse continues unabated, leading to the formation of a singularity. This singularity is a point in space where the density becomes infinite, and the laws of physics as we know them cease to apply. This point of infinite density is surrounded by an event horizon, the boundary beyond which nothing can escape the gravitational pull, not even light. The gravitational pull of a black hole is so strong that it warps the fabric of space and time around it, creating a region from which escape is impossible. This is why black holes appear black. They trap all light that comes too close. Thus, a black hole is born, a cosmic enigma that continues to captivate scientists and astronomers alike, offering a glimpse into the most extreme conditions in the universe. Neutron stars are another possible outcome of stellar death. These are the remnants of stars that were not quite massive enough to become black holes but still underwent a dramatic collapse. These stars, slightly less massive than those that form black holes, end their lives in a supernova explosion as well, but the result is different. The collapse of these stars is halted by neutron degeneracy pressure, a quantum mechanical effect that arises when neutrons are packed so closely together that they resist further compression. This creates an object incredibly dense, so much so that a single teaspoon of neutron star material would weigh billions of tons on Earth. Neutron stars are fascinating in their own right, with magnetic fields trillions of times stronger than Earth's and the ability to spin at incredible speeds. Some neutron stars become pulsars, emitting beams of radiation that sweep across space like cosmic lighthouses. These beams can be detected from Earth, providing valuable insights into the nature of these extreme objects. Both black holes and neutron stars are testament to the incredible processes that govern the life and death of stars. They remind us of the dynamic and ever-changing nature of the universe, where even in death, stars can give birth to some of the most extraordinary phenomena known to science. Pulsar timing involves measuring the arrival times of pulses from pulsars with extreme accuracy. Pulsars are rotating neutron stars that emit beams of electromagnetic radiation, and as these beams sweep across Earth, we observe them as regular pulses. Pulsars emit pulses at very regular intervals, making them some of the most stable clocks in the universe. However, their periods can change slightly due to various astrophysical effects. The exact moment when each pulse is detected is recorded. Over time, these TOAs are used to construct a timing model for the pulsar. After fitting a timing model to the data, any deviations from the expected arrival times, known as residuals, can reveal information about the pulsar itself, its environment, or external influences like gravitational waves. Observations are conducted using radio telescopes, with each pulse's arrival time recorded relative to an Earth-based time standard. Pulsar timing involves linking pulses over long timescales to account for pulse-to-pulse variations and modeling the pulsar's rotation, proper motion, and other effects like interstellar medium dispersion. Adjustments are made for the delay caused by the interstellar medium, which affects different radio frequencies differently, and for temporal and spatial variations due to the interstellar medium. Binary pulsar systems like PSRB 1913+16 have been used to confirm predictions of general relativity, including the emission of gravitational waves. Timing observations help in measuring the masses of neutron stars, studying their internal structure, and understanding phenomena like pulsar glitches. Networks of pulsars are monitored to detect the gravitational wave background from supermassive black hole binaries. Anomalies in timing could be due to these low-frequency gravitational waves. In the future, pulsars could serve as celestial GPS for deep space missions due to their regularity. Pulsars can help in calibrating cosmic distances through their dispersion measures. Pulsars in binary systems with planets can show timing variations due to the planet's orbits. Changes in the medium through which the pulses travel can distort arrival times, and some pulsars exhibit timing noise which can be intrinsic to the pulsar, complicating long-term timing models. For pulsars in binary systems, accurately modeling the orbit and its effects on pulse arrival times is complex. Achieving the necessary precision requires sophisticated instrumentation and data reduction techniques. Instruments like the Square Kilometre Array will dramatically increase the number of observable pulsars and enhance the precision of timing observations. Continuous improvement in data analysis techniques, including machine learning for pattern recognition and timing residuals, is ongoing. Combining radio timing with observations in X-ray, gamma ray, or optical can provide a more comprehensive understanding of pulsar behavior. Pulsar timing observations exemplify how precision astronomy can push the boundaries of our understanding, from the behavior of matter under extreme conditions to the very fabric of space-time itself. Section 4 echoes from the void, observing the invisible. Black holes are invisible, they emit no light. So how do we know they exist? We observe their effects on their surroundings. One way is by observing the motion of stars. Stars orbiting an invisible, massive object suggest a black hole's presence. The speed of these stars, their orbits, tell us about the unseen object's mass. Another way is by detecting X-rays. As matter falls into a black hole, it heats up. This superheated material emits X-rays detectable by our telescopes. These X-ray emissions provide evidence of black holes. Gravitational waves offer more proof. These ripples in spacetime are produced by violent cosmic events. The collision of two black holes is one such event. Albert Einstein predicted their existence in 1916 as part of his theory of general relativity. Detecting these waves confirms Einstein's theory and provides more evidence for the existence of black holes. Section 5. Unraveling the Cosmos, Black Holes and the Fabric of Reality. Black holes are not just celestial objects, they are cosmic laboratories, offering a unique window into the most extreme conditions in the universe. These enigmatic entities challenge our understanding of the cosmos and push the boundaries of modern physics. They offer insights into the fundamental laws of physics, providing a testing ground for theories that govern the universe. Scientists around the world dedicate their lives to studying these mysterious phenomena, hoping to unlock the secrets they hold. Their extreme conditions test the limits of our understanding. The immense gravitational forces at play in and around black holes create environments unlike any other, allowing us to observe the effects of gravity in its most intense form. Einstein's theory of general relativity describes gravity as the curvature of spacetime. This revolutionary idea transformed our understanding of gravity, moving away from the Newtonian concept of a force acting at a distance. Black holes, with their immense gravity, warp spacetime significantly. This warping effect is so strong that it can bend light, creating phenomena such as gravitational lensing, where the light from distant stars is bent around the black hole, magnifying and distorting the images we see. They create a cosmic well, a region where the gravitational pull is so strong that not even light can escape. This event horizon marks the boundary beyond which nothing can return. making black holes appear as dark voids in the fabric of space. Studying black holes could help us unify general relativity with quantum mechanics. These two pillars of modern physics describe the universe on vastly different scales: general relativity on the cosmic scale and quantum mechanics on the subatomic scale. These are the two pillars of modern physics. Currently, they are incompatible. The quest to reconcile these theories is one of the greatest challenges in physics, and black holes might hold the key to this unification. Black holes might hold the key to a unified theory. By studying the behavior of matter and energy in these extreme environments, scientists hope to uncover a theory that seamlessly integrates the principles of both general relativity and quantum mechanics. The information paradox is another puzzle. This paradox arises from the question of what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but black holes seem to defy this principle. What happens to information that falls into a black hole? Does it disappear? This question challenges our understanding of information conservation, a fundamental principle in physics that states information about a physical system should always be preserved. This question challenges our understanding of information conservation. Resolving the information paradox could lead to groundbreaking discoveries about the nature of reality and the fundamental laws that govern the universe. Black holes push us to the frontiers of knowledge. They compel us to explore the deepest questions about the universe, from the nature of space and time to the behavior of matter and energy under extreme conditions. They force us to confront the biggest questions about the universe and our place in it. As we continue to study black holes, we move closer to understanding the true nature of reality and our role within the vast cosmos. Pause 2S, Section 6, The Mysterious World of Black Holes, a Deep Dive. As we venture further into the enigmatic realm of black holes, we uncover layers of complexity that intertwine science and theology, offering a holistic perspective on these celestial wonders. Pause 1S. Formation. Black holes are born from the remnants of massive stars that have exhausted their nuclear fuel. When a star undergoes a supernova explosion, the core collapses under the force of its own gravity, forming a black hole. There are also primordial black holes, theorized to have formed in the early universe, and supermassive black holes which reside at the centers of galaxies, often formed through mergers and accretion of mass over billions of years. Pause 1S. Properties. A black hole's defining feature is its event horizon, the point beyond which nothing can escape its gravitational pull. At its core lies the singularity, a point of infinite density where the laws of physics as we know them cease to apply. Black holes also emit Hawking radiation, a theoretical prediction that they can lose mass and energy, eventually evaporating over time. The no-hair theorem simplifies black holes to three observable properties: mass, charge, and spin. Pause 1S. Observational evidence. We detect black holes indirectly through their interactions with surrounding matter. X-ray emissions from accretion disks, gravitational waves from black hole mergers, and the activities of quasars and galactic centers all provide compelling evidence of their existence. These phenomena reveal the dynamic and often violent nature of the cosmos. Pause 1S. Theoretical implications. Black holes challenge our understanding of the universe. They serve as testing grounds for general relativity and quantum mechanics, two pillars of modern physics that remain incompatible. The information paradox, which questions the fate of information that falls into a black hole, pushes the boundaries of our comprehension, suggesting that new physics may be required to resolve these mysteries. Pause 1S. Cultural and theological reflection. The wonders of black holes are not confined to the realm of science. Many find parallels between these cosmic phenomena and ancient texts, such as the Quran. Verses that speak of creation, destruction, and the nature of time and space resonate with the scientific understanding of black holes, emphasizing the divine signs in the universe and the limits of human knowledge. Pause 1S. In conclusion, black holes offer a profound and multifaceted glimpse into the workings of the cosmos. They challenge us to expand our horizons, bridging the gap between science and spirituality, and inviting us to ponder the mysteries that lie at the heart of existence. Pause 2S. As we continue to explore these cosmic enigmas, we are reminded of our place in the vast universe and the endless quest for knowledge that defines our very essence. Pause 2S. Section 7. Neutron stars, cosmic beacons. As we continue our journey through the cosmos, we turn our attention to another marvel: neutron stars. These celestial objects, born from the remnants of massive stars, are among the densest and most intriguing entities in the universe. Pause 1s. Formation. Neutron stars are the result of core collapse supernovae in stars of sufficient mass. During this cataclysmic event, the outer layers of the star are ejected into space while the core collapses under gravity, leading to an extremely dense remnant. Pause 1s. Properties. Neutron stars boast incredible density, often packing more mass than the Sun into a sphere just a few kilometers in diameter. They also exhibit strong magnetic fields and rapid rotation, and their unique internal structure may include exotic matter states such as quark matter. Pause 1s. Observational phenomena. These stellar remnants manifest in various forms, including pulsars, which emit regular pulses of radio waves, X-rays, or even gamma rays. Millisecond pulsars spin hundreds of times per second, while magnetars possess extraordinarily powerful magnetic fields. Neutron stars also contribute to gravitational wave astronomy, as their mergers produce detectable ripples in spacetime. Pause 1s. Theoretical and practical implications. Neutron stars serve as natural laboratories for extreme physics, offering insights into nuclear physics, quantum mechanics, and general relativity. Their study helps us understand the behavior of matter under extreme conditions, pushing the boundaries of our scientific knowledge. Pause 1s. Theological and philosophical considerations. Though neutron stars are not directly mentioned in the Quran, they can be seen as part of the broader cosmic order. Their existence reflects divine power and the complexity of creation, inviting us to marvel at the intricate and wondrous universe in which we live. Pause 1s. In conclusion, neutron stars, with their unique properties and profound implications, continue to captivate scientists and philosophers alike. They remind us of the vast interconnected web of the cosmos and our ongoing quest to understand the universe's deepest mysteries. Pause 2s. As we delve deeper into the wonders of the night sky, we are continually reminded of our small yet significant place in the grand tapestry of existence. Pause 2s. Section 8. Bridging Science and Spirituality. As we conclude our exploration of cosmic wonders, it's essential to reflect on the deeper connections between science and spirituality. Both black holes and neutron stars, with their awe-inspiring phenomena, serve as profound sources of contemplation and inspiration, aligning with Islamic teachings on the pursuit of knowledge as a form of worship. Pause 1s. Integration and interpretation. The Quran's metaphorical language often invites us to ponder the mysteries of the universe. While caution is necessary to avoid literal interpretations, such reflections can lead to a harmonious blend of scientific inquiry and spiritual insight. Pause 1s. Cultural impact. These celestial phenomena have the power to influence art, literature, and education within Islamic contexts. They promote a narrative where science and spirituality are not at odds, but are seen as complementary aspects of human understanding. Pause 1s. Educational value. Encouraging scientific inquiry as a religious obligation can shape educational curricula to reflect both scientific achievement and spiritual growth. This dual approach fosters a well-rounded perspective, enriching the minds and souls of future generations. Pause 1s. Challenges. Balancing metaphorical interpretations with scientific facts is crucial. Avoiding anachronistic readings of religious texts while fostering a respectful dialogue between science and spirituality ensures the integrity of both domains is maintained. Pause 1s. Conclusion. Studying black holes and neutron stars through a Quranic lens exemplifies the potential for harmony between Islamic theology and modern science. It invites believers to explore the universe's mysteries as a form of spiritual practice, emphasizing the unity of knowledge under the principle of Tawhid. Pause 1s. This exploration not only enhances our scientific understanding but also deepens our spiritual connection to the Creator, recognizing the vastness of His creation. However, this dialogue must be approached with care to uphold the integrity of both scientific inquiry and religious text interpretation. Pause 1s. Neutron star mergers represent one of the most spectacular and informative events in astrophysics. They offer profound insights into extreme physics, the behavior of matter under intense conditions, and the processes that shape our understanding of the universe. Pause 2s. As we continue to gaze upon the night sky, let us remain mindful of our small yet significant place in this grand tapestry of existence, ever curious and ever humble. Pause 2s. Section 9. Theoretical and Observational Challenges. As we delve deeper into the enigmatic phenomena of neutron stars, we encounter numerous theoretical and observational challenges that push the boundaries of our current scientific understanding. Simulation complexity. Modeling neutron star mergers requires advanced numerical simulations that account for general relativity, magnetohydrodynamics, and nuclear physics. These simulations are crucial for predicting the behavior of matter under extreme conditions and for understanding the intricate dynamics of these cosmic events. Detectability. While gravitational waves from neutron star mergers are now detectable, capturing their electromagnetic counterparts requires rapid follow-up observations across the globe and in space. This coordinated effort is logistically challenging but essential for a comprehensive understanding of these events. Neutron star mass. Determining the fate of the merged object, whether it forms a hypermassive neutron star that later collapses into a black hole or directly forms a black hole, depends on the total mass of the system. This remains an area of active study, with each discovery bringing us closer to understanding these celestial giants. Future directions: multi-messenger astronomy, combining gravitational wave signals with electromagnetic observations including light, X-rays, gamma rays, and potentially neutrino detection, will provide a more complete picture of these events. This approach, known as multi-messenger astronomy, holds the promise of unlocking new cosmic secrets. Next-generation observatories. Future gravitational wave detectors like the Einstein telescope or Cosmic Explorer will be more sensitive, detecting more mergers at greater distances and with higher precision. These advancements will significantly enhance our ability to study neutron star mergers. Theoretical advancements. Continued refinement of our understanding of neutron star interiors, the equation of state, and the physics of high-energy processes in these mergers will come from both theoretical work and observational data. These efforts will deepen our knowledge of the universe's evolution, the distribution of elements, and the fundamental laws governing matter and gravity. The equation of state, EOS, for neutron stars is a crucial concept in astrophysics, describing how the pressure of the star's matter changes with its density and temperature. This relationship is fundamental for understanding the internal structure, stability, and observable properties of neutron stars. Importance of the neutron star EOS. Internal structure. The EOS determines how matter behaves under the extreme conditions inside a neutron star, where densities can exceed those found in atomic nuclei. Mass-radius relationship. Different EOSs predict different maximum masses and radii for neutron stars. Observations of these parameters can help constrain the EOS, neutron star mergers. The EOS affects the outcome of neutron star mergers, whether they result in a stable neutron star, a temporary hypermassive neutron star, or directly collapse into a black hole. Astrophysical phenomena. The EOS influences phenomena like pulsar glitches, starquakes, and the emission properties of neutron stars. Key aspects of neutron star EOS. Phases of matter. As density increases, crust. The outer layers have a structure akin to nuclear pasta, due to competition between nuclear forces and Coulomb repulsion. Inner crust. Here, neutron drip occurs where free neutrons start to appear outside atomic nuclei. Outer core, largely composed of neutrons with some protons and electrons. Inner core could contain exotic states like hyperons, pion or kaon condensates, or even quark matter. Nuclear forces. The EOS depends heavily on nuclear interactions, including strong nuclear force, governs the behavior of nucleons at short distances. Weak nuclear force, relevant for beta equilibrium in neutron stars. Relativistic effects. At the high densities of neutron stars, general relativity must be accounted for in the EOS. Quantum effects. Quantum mechanics plays a significant role, especially with phenomena like superfluidity and superconductivity in neutron star interiors. Theoretical models, non-relativistic models. These include Scherm interactions where the nuclear potential is parameterized to fit known nuclear data. Relativistic mean field, RMF models. These incorporate relativistic effects explicitly, often using meson exchange to describe nuclear forces. Quark models. At the highest densities, quarks might no longer be confined within nucleons, leading to models like the MIT bag model or perturbative QCD, hybrid models. These consider a transition from nuclear matter to quark matter at some critical density. Observational constraints, mass measurements. Pulsar timing, particularly in binary systems, provides precise mass measurements which the EOS must predict. Radius measurements. Observations like those from NICER, Neutron Star Interior Composition Explorer, attempt to measure neutron star radii, constraining the EOS. Gravitational waves. The tidal deformability observed during neutron star mergers with gravitational wave detectors like LIGO, Virgo, gives insights into the EOS. Neutrino emissions. Neutrinos from neutron star cooling or from supernova events can inform us about the EOS. Challenges. Uncertainty in nuclear physics. The behavior of nuclear matter at densities above those found in atomic nuclei is not well constrained by terrestrial experiments. Phase transitions. The possibility of phase transitions to exotic matter states complicates the EOS. Computational complexity. Simulating the behavior of matter at neutron star densities requires sophisticated numerical methods, often involving approximations. Future directions. Advanced observations, upcoming missions like Athena, will push the boundaries of our observational capabilities, providing more data on neutron stars. Laboratory experiments. Facilities like the Facility for Rare Isotope Beams, FRIB, aim to study nuclear matter at higher densities, potentially informing neutron star EOS. Theoretical developments. Continued refinement of models with inputs from quantum chromodynamics, QCD, calculations and lattice QCD simulations. The neutron star equation of state remains an open question in physics, where each new observation or theoretical breakthrough can significantly refine our understanding of these cosmic phenomena. As we continue to investigate these celestial enigmas, we edge closer to unraveling the mysteries of the universe, one discovery at a time. As we transition from the theoretical and observational challenges, we delve into the broader implications of studying neutron stars. These celestial bodies serve as natural laboratories for exploring the fundamental laws of physics under extreme conditions. Neutron stars provide unique insights into how does matter behave at nuclear densities. The extreme environments inside neutron stars push our understanding of quantum mechanical phenomena to new limits. Neutron stars test theories of gravity, particularly in strong gravitational fields. Observing these stars helps refine our understanding of Einstein's theories. The equation of state of neutron star matter remains a critical area of study. Understanding this relationship is key to comprehending the internal structure and stability of these stars. Neutron stars also play a vital role in broader astrophysical contexts. They help us understand the life cycles of stars and the distribution of stellar remnants across galaxies. In binary systems, neutron stars can gain mass and become X-ray binaries, leading to further stellar phenomena and enriching the cosmic environment. Observations of neutron stars contribute to our understanding of the universe's composition, including the influence of dark matter on galaxy structures. Technological advancements have significantly enhanced our ability to study neutron stars. Instruments like Chandra, XMEM, Newton, and Fermi have mapped neutron stars across various wavelengths, providing detailed data on their emissions and environments. With detectors like LIGO and Virgo and future missions such as LISA, we are now observing neutron star mergers. These observations offer unprecedented data on the nature of neutron stars and the physics of gravity. Future neutrino observatories might detect neutrinos emitted by neutron stars, offering another window into their internal processes. Upcoming missions like Athena will push the boundaries of our understanding further, observing neutron stars with unparalleled detail. Neutron stars, with their extreme conditions and unique properties, continue to challenge and expand our understanding of the universe. They are not just cosmic remnants but are fundamental to advancing our knowledge of the laws that govern the cosmos. As we conclude our exploration of the universe's most enigmatic phenomena, we turn our gaze to one of the most profound discoveries in cosmology, the cosmic microwave background, or CMB. The age of the universe is estimated at about 13.8 billion years, and the CMB offers a glimpse into its infancy just 380,000 years after the Big Bang. This ancient light serves as a cosmic fingerprint revealing the universe's composition, including dark energy, dark matter, and baryonic matter. The expansion rate of the universe, quantified through the Hubble constant, is intricately linked to the CMB. By studying the minute fluctuations in this primordial radiation, scientists can test various cosmological models, probing the origins and evolution of the universe, including the elusive dark matter and dark energy theories. The CMB also provides crucial insights into the early universe physics, offering clues about conditions before the formation of the first stars. This ancient radiation allows us to explore energies unattainable by current particle accelerators, pushing the boundaries of our understanding. However, studying the CMB comes with its challenges and future prospects. Removing the foreground signals from the galactic and extragalactic sources to isolate the CMB is a technically demanding task. Precision measurements are essential, with future observations aiming to detect even the faintest signals, such as B-mode polarization from cosmic inflation. Next-generation experiments like CMB-S4 aim to map the CMB with unprecedented detail, while space missions such as Lightbird will focus on polarization to delve deeper into cosmic inflation. These efforts will address theoretical challenges, including discrepancies between CMB data and other cosmological observations, hinting at physics beyond current models. The cosmic microwave background is not merely a relic of the Big Bang, it is an ongoing source of discovery. It helps us piece together the history, structure, and fate of the universe, continually refining our cosmological understanding and pushing the limits of what we know about the cosmos. As we venture further into the realms of the unseen and the unknown, the CMB stands as a beacon, guiding us through the cosmic tapestry and reminding us of the universe's grand and mysterious origins. As we delve deeper into the cosmos, we encounter some of the most fascinating and enigmatic objects, pulsars. These are neutron stars that emit beams of radiation, creating a lighthouse effect as they rotate. When one of these beams crosses our line of sight, we detect a pulse of radiation, hence the name pulsar. Pulsars come in various types, each offering unique insights into the universe's mechanics. Radio pulsars are the most commonly detected, emitting in the radio spectrum. They serve as cosmic clocks, their precise pulses allowing scientists to test theories of gravity and the interstellar medium. X-ray pulsars are often found in binary systems where they accrete matter from a companion star, heating it to X-ray temperatures. These pulsars provide a window into the extreme physics of matter under intense gravitational and magnetic fields. Millisecond pulsars are old pulsars that have been spun up by accreting mass from a companion star, leading to incredibly fast rotation rates. These pulsars help us understand the end stages of stellar evolution and the recycling process in binary systems. Magnetars are a subclass of pulsars with magnetic fields so strong that they power bursts of gamma rays and X-rays, rather than the typical radio emissions. They are associated with fast radio bursts, FRBs, and soft gamma repeaters, offering clues to some of the most energetic phenomena in the universe. Beyond electromagnetic radiation, neutron stars also reveal their secrets through gravitational waves. Neutron star mergers observed through gravitational waves by detectors like LIGO and Virgo provide unprecedented insights into the behavior of matter under extreme gravity. These cosmic collisions also shed light on the origins of heavy elements via the R process nucleosynthesis. Pulsars and gravitational waves are not merely cosmic curiosities, they are profound tools that help us probe the very fabric of space-time, enhancing our understanding of the universe's most extreme environments. As we continue to observe and study these phenomena, we inch closer to unraveling the mysteries that govern our cosmos. As we look forward to the future, the study of neutron stars promises even more groundbreaking discoveries. One of the foremost instruments in this endeavor is the Neutron Star Interior Composition Explorer, or NICER, located on the International Space Station. This innovative tool measures X-ray emissions from neutron stars, offering unprecedented precision in studying their mass, radius, and surface characteristics. Advancements in computational power are also playing a pivotal role. Detailed simulations of neutron stars from their formation to their eventual decay or merger are helping to refine theories about their internal structure. These theoretical models are crucial in bridging the gap between observation and our understanding of extreme physics. CubeSat missions are another exciting development. These small, cost-effective satellites like BurstCube are being developed to catch gamma-ray bursts from neutron star mergers or magnetar flares. Their deployment will expand our observation capabilities, allowing us to capture and study these fleeting cosmic events in greater detail. Neutrino telescopes, such as IceCube, are on the lookout for neutrinos emanating from neutron stars. These elusive particles could reveal new aspects of the internal processes within neutron stars, offering a different perspective on their complex inner workings. Deep field observations using advanced telescopes like the James Webb Space Telescope will enable us to conduct deeper and longer observations. This might reveal faint neutron stars or their remnants in distant galaxies, enhancing our understanding of neutron star populations across cosmic history. Neutron stars continue to be at the forefront of astrophysical research. They challenge our understanding of physics, providing a bridge between the atomic scale and the cosmic scale where the laws of physics are pushed to their limits. The future of neutron star research is bright, promising to unravel more of the universe's deepest mysteries. The Big Bang Theory is the prevailing cosmological model for the observable universe's origins and development from an extremely hot and dense state about 13.8 billion years ago. Here's an exploration of this theory in relation to scientific understanding and its echoes in religious texts like the Quran, discovered in 1965 by Arno Penzias and Robert Wilson. The CMB is the thermal radiation left over from the time when the universe was in a hot, dense state. It's considered strong evidence for the Big Bang. Edwin Hubble's observations in the 1920s showed that galaxies are moving away from each other, leading to the conclusion that the universe is expanding. This implies that at some point in the past, everything was much closer or even in a single point, the Big Bang. The theory explains the observed cosmic abundances of hydrogen, helium, and lithium, which were formed during the first few minutes after the Big Bang in a process known as Big Bang nucleosynthesis. A refinement of the Big Bang model, cosmic inflation suggests there was a rapid expansion of space itself in the very early universe, explaining the large-scale uniformity of the cosmos. The earliest moments where quantum effects of gravity are significant, with no clear understanding due to the lack of a complete theory of quantum gravity. When the fundamental forces were unified, a brief period of exponential expansion. Quarks and gluons were free before they formed hadrons, formation of protons and neutrons from quarks. Electrons and positrons annihilate each other, leaving behind a small number of electrons, and nucleosynthesis occurs, dominated by photons until matter starts to dominate, when matter begins to dominate over radiation. When the universe had cooled enough for electrons to combine with nuclei, forming neutral atoms, allowing photons to travel freely, CMB, gravity causes matter to start clumping together, leading to galaxies, stars, etc. This scientific narrative finds intriguing echoes in the Quran, where verses like Surah Al-Anbiya 21:30 state, "Have those who disbelieve not considered that the heavens and the earth were a joined entity, and we separated them?" Such verses are often interpreted to align with the Big Bang concept, showcasing a fascinating intersection between ancient text and modern cosmology. Quranic cosmology, or the understanding of the cosmos as described or implied in the Quran, is a field where ancient text meets modern interpretation. Here's an exploration of how the Quran's verses are often discussed in relation to cosmology. Key Quranic concepts in cosmology: creation of the universe. Surah Al-Anbiya 21:30 states, "Have those who disbelieved not considered that the heavens and the earth were a joined entity, and we separated them?" This verse is often interpreted as an allusion to the Big Bang theory, where the universe expanded from a single point. Similarly, Surah Fussilat 41:11 mentions, "Then he directed himself to the heaven while it was smoke, and said to it and to the earth, 'Come into being, willingly or by compulsion.'" The term smoke here is sometimes linked to the state of the early universe, filled with gas and dust. Expansion of the universe. Surah Ad-Dariyat 51:47 says, "And the heaven we constructed with strength, and indeed, we are its expander." This verse is cited as a possible reference to the expanding universe, a theory proposed by Edwin Hubble in the 20th century. Orbits and celestial bodies. Surah Yasin 36:38-40 describes, "And the sun runs on course toward its stopping point. That is the determination of the exalted in might, the knowing. And the moon, we have determined for it phases until it returns, appearing like the old date stalk. It is not for the sun to overtake the moon, nor does the night outstrip the day. They all float, each in an orbit." These verses are interpreted to describe the orbits of celestial bodies, including the sun and moon, and their independent paths, aligning with modern astronomical understanding. Multiverse or multiple heavens. Surah Al-Mulk 67:3 states, "And he is the one who created 7 heavens in layers." Some scholars interpret this to mean either different levels of heaven in a spiritual sense or, more speculatively, as a reference to multiple universes or dimensions in modern physics. End of the universe. Surah Al-Anbiya 21:104 mentions, "The day when we will fold the heaven like the folding of a written sheet for the records. As we began the first creation, we will repeat it. That is a promise binding upon us. Indeed, we will do it." This could be seen as an analogy for the end of the universe, perhaps akin to what physicists call the Big Crunch, or a cyclic model of the universe. Through these verses, the Quran offers a rich tapestry of ideas that intersect with modern cosmological theories, providing a unique perspective on the origins, structure, and fate of the cosmos. Comparing black holes with the Big Bang involves looking at two very different concepts within cosmology and astrophysics, one dealing with the end of stellar life cycles, and the other with the origin of the universe itself. Here's how they contrast and connect. Black holes, nature, formation. Black holes form from the gravitational collapse of massive stars or potentially from the collapse of dense regions in the early universe, primordial black holes. Structure, event horizon, the boundary beyond which nothing can escape the black hole's gravity. Singularity, the point of infinite density where all matter is compressed, according to general relativity, though quantum mechanics suggests this might not be the entire story. Properties, mass, charge, spin, characterized by mass, electric charge, and angular momentum, but nothing else, no Hare theorem. Hawking radiation. Black holes emit radiation due to quantum effects, leading to their eventual evaporation over vast timescales. Observational evidence, astrophysical, detected through their gravitational effects on nearby matter, X-ray emissions from accretion disks, or gravitational waves from black hole mergers. Cosmological impact, galaxy dynamics, supermassive black holes at galaxy centers influence galaxy evolution through their gravity and activity. Big Bang, nature, event. The Big Bang theory describes the universe's origin from an extremely hot, dense state about 13.8 billion years ago. Expansion. The universe has been expanding since this initial explosion, as evidenced by the redshift of light from distant galaxies and the cosmic microwave background radiation. Phases. Early universe. Involved various epochs like inflation, Quark-Gluon plasma, nucleosynthesis, etc., each with different physical processes dominating. Singularity. The Big Bang might have started from a singularity, but this is more speculative due to our lack of understanding of quantum gravity at that scale. Observational evidence, cosmic microwave background, CMB, leftover radiation from when the universe cooled enough for atoms to form. Large-scale structure. The distribution of galaxies and the cosmic web provide evidence of the Big Bang's aftermath. Cosmological impact, universe's evolution. The Big Bang sets the initial conditions for all of cosmology, from the formation of the first elements to the eventual structure of the universe. Comparisons and connections, singularity. Both concepts involve singularities where the laws of physics as we understand them break down. However, the Big Bang singularity is at the beginning of space-time, while black hole singularities are within space-time, time and space. Black holes warp space-time to such an extent that they create regions from which nothing can escape, potentially leading to the end of time for anything falling into them. The Big Bang is where space-time itself might have begun, expanding from a point of infinite density. Quantum mechanics and gravity. Both scenarios challenge our understanding of physics. Black holes test the limits of quantum mechanics with phenomena like Hawking radiation. The Big Bang probes quantum gravity, where we need a theory to reconcile general relativity with quantum mechanics. Matter and energy. Black holes are regions where matter and energy are concentrated to extreme levels. The Big Bang describes how matter and energy were once uniformly distributed across space before clumping into structures. Cosmic recycling. Black holes might recycle matter and energy back into the universe via Hawking radiation, while the Big Bang can be seen as the ultimate recycling event, creating all matter from energy. End versus beginning. Black holes represent an endpoint for matter in the universe, whereas the Big Bang represents the starting point for the universe's matter and energy. Philosophical considerations. While black holes are often discussed in terms of destruction or information loss, the Big Bang is about creation, the beginning of everything we observe. In summary, while black holes and the Big Bang both involve singularities and extreme conditions of spacetime, they represent opposite ends of cosmic narratives. One, the violent end of cosmic structures; the other, the explosive birth of the cosmos itself. Both push the boundaries of our comprehension of physics, particularly where general relativity meets quantum mechanics. Through a Quranic lens, both black holes and the Big Bang theory can be subjects of interpretation, reflection, and sometimes controversy. Here's how these scientific concepts might be viewed or connected to Quranic narratives. Black holes, creation and destruction. Surah Al-Waqi'ah 56:75-76 mentions the setting places of the stars, which might be interpreted as an analogy for black holes, where stars end their life cycles. This aligns with the notion of creation and destruction being part of the cosmic cycle, a theme that resonates with the Islamic concept of the universe having a beginning and an end. The unseen and the known, black holes being invisible and only detectable through their effects, can be seen as a metaphor for the unseen aspects of the universe that Allah alone knows fully. Surah Al-Mulk 67:3 speaks of 7 heavens, which some interpret as layers or dimensions of existence, potentially including phenomena like black holes. End of time. The idea of an event horizon where time and space behave differently could be metaphorically linked to the Quranic descriptions of the Day of Judgment, where time will end or be judged differently, as suggested in Surah Al-Anbiya 21:104, speaking of folding the heavens like a scroll. Big Bang, origin of the universe, Surah Al-Anbiya 21:30 states, "The heavens and the earth were a joined entity, and we separated them." This verse is often cited as a Quranic parallel to the Big Bang, where the universe expanded from a single point. It suggests a divine act of separation or creation from a unified state. Expansion of the universe, Surah Ad-Dariyat 51:47 says, "And the heaven we constructed with strength, and indeed we are its expander." This is interpreted by some as an early mention of the expanding universe, a key aspect of the Big Bang theory. Creation from smoke, Surah Fussilat 41:11 mentions, "Then he directed himself to the heaven while it was smoke, and said to it and to the earth, 'Come into being, willingly or by compulsion.'" The smoke can be likened to the pre-stellar gas clouds in the early universe or the hot, dense state before expansion. These verses provide a fascinating intersection of science and spirituality, offering a unique perspective on the mysteries of the cosmos. Whether seen as metaphorical or literal, they invite deep reflection on the nature of creation and the universe. The Big Bang Theory, in the context of the Quran creation from a single point, Surah Al-Anbiya 21:30 states, "Have those who disbelieved not considered that the heavens and the earth were a joined entity, and we separated them?" This verse has been interpreted by some as an allusion to the universe expanding from a single point, much like the Big Bang. Expansion of the universe, Surah Ad-Dariyat 51:47, says, "And the heaven we constructed with strength, and indeed we are its expander." This verse is often cited as a Quranic reference to an expanding universe, aligning with Hubble's observations. Creation from smoke, Surah Fussilat 41:11 mentions, "Then he directed himself to the heaven while it was smoke, and said to it and to the earth, 'Come into being, willingly or by compulsion.' They said, 'We have come willingly.'" The term smoke has been linked to the state of the early universe, filled with gas and dust before stars formed. Interpretations and considerations, scientific miracles. Some scholars claim these verses indicate scientific knowledge in the Quran far before these concepts were known by science, positing the idea of scientific miracles in the text. Metaphor versus science. Others argue that these interpretations might be too literal, emphasizing that the Quran's language is often metaphorical, aimed at spiritual guidance rather than scientific description. Cultural and historical context. Given the time when the Quran was revealed, such interpretations must be approached with an understanding of the language, culture, and knowledge of that era. Interdisciplinary dialogue. Discussions around these verses highlight the intersection of religion and science, where some see harmony, while others maintain a clear distinction between the two domains. Conclusion. The Big Bang Theory as a scientific model stands on rigorous observational and theoretical foundations, independent of religious texts. However, for those who engage in the study of both science and religion, the Quran's verses provide a fascinating point of reflection on the nature of creation, often seen in a complementary light to scientific understanding, though this is not universally accepted and remains a subject of debate and interpretation within Islamic scholarship. Binary systems and mass exchange. X-ray binaries. When a neutron star is in a close binary with a normal star, matter can flow from the companion to the neutron star, creating an accretion disk. This disk heats up, emitting X-rays, and can lead to the star being spun up or recycled into a millisecond pulsar. Type 1 X-ray bursts. These are caused by runaway nuclear fusion on the surface of the neutron star when enough hydrogen or helium accumulates from the companion star. Low-mass X-ray binaries, LMXBs, and high-mass X-ray binaries, HMXBs. These systems differ based on the mass of the donor star, with LMXBs often leading to the creation of millisecond pulsars. Neutron star mergers, gravitational wave signals. The merger of two neutron stars was first observed through gravitational waves by LIGO and Virgo in 2017, GW170817. This event not only confirmed theoretical predictions but also provided a wealth of data on neutron star physics, the equation of state, tidal deformability, and the maximum mass of neutron stars. Nucleosynthesis, the R process responsible for creating heavy elements like gold and platinum. Multi-messenger astronomy combining gravitational waves with electromagnetic observations to study the same event. Kilonovae, these are the optical/UV/infrared counterparts to neutron star mergers, characterized by their unique light curves and spectra, which are rich in elements formed in the R process. As we journey further into the depths of the cosmos, we encounter a state of matter so extreme and so ancient that it takes us back to the very moments after the Big Bang, the Quark-Gluon plasma, or QGP. This exotic state existed when the universe was just microseconds old, where quarks and gluons, the fundamental building blocks of protons and neutrons, roamed freely in a superheated, dense environment. QGP is not just a relic of the past, it's a window into the universe's infancy, offering unparalleled insights into the conditions that shaped everything we see today. But what exactly is QGP, and how do scientists study it? Lattice QCD simulations on supercomputers help us understand how quark matter might behave at densities relevant to neutron stars or black holes. These simulations are crucial for predicting the properties of QGP and studying the phase transition from hadronic matter to this primordial plasma. High-energy physics experiments, such as those conducted at the Large Hadron Collider, LHC, recreate conditions similar to those just after the Big Bang. Here, quark-gluon plasma is briefly observed, providing a fleeting but invaluable glimpse into this extreme state of matter. Theoretical models propose various scenarios, including the possibility that the core of a black hole might not be a true singularity, but a highly compressed state of matter, potentially including quark phases. These models push the boundaries of our understanding, challenging us to unify quantum mechanics with general relativity to describe what happens to quarks in such extreme environments. However, the study of QGP is fraught with challenges. The physics inside a black hole or at densities where quarks might deconfine are beyond our current experimental reach on Earth. Moreover, the preservation or loss of quarks' quantum information in a black hole remains a significant theoretical puzzle. Despite these challenges, the study of QGP is at the frontier of theoretical physics. It's a field ripe with speculation, requiring advances in both theoretical models and observational capabilities to unravel its mysteries. QGP is believed to form at temperatures above approximately 2 trillion degrees Kelvin, conditions last seen microseconds after the Big Bang. This extreme state can be recreated in high-energy particle collisions, particularly at facilities like the RHIC and LHC. Here, experiments such as ALICE, ATLAS, and CMS study heavy ion collisions to observe the signatures of QGP. Experimental signatures like jet quenching, elliptic flow, and strangeness enhancement provide indirect evidence of QGP. These signals require sophisticated analyses to distinguish from other effects in high-energy collisions. Theoretical aspects, including lattice QCD and the QCD phase diagram, help us map out the transition from ordinary nuclear matter to QGP. Understanding this phase transition offers insights into cosmology, neutron stars, and high-energy physics. However, QGP exists for an extremely short time in experiments, making direct observation challenging. Future directions include improved detectors, advancements in QCD theory, and multi-messenger astronomy to offer indirect evidence or constraints on QGP in neutron stars. The quark-gluon plasma is a testament to the universe's violent and dynamic past. It bridges the gap between the smallest particles and the grandest cosmic structures, reminding us that the universe's story is far from fully written. As we continue to explore this primordial state, we move one step closer to understanding the very fabric of our existence. As we delve deeper into the cosmos, we encounter two of the most profound phenomena that challenge our understanding of the universe: the Big Bang and black holes. Though they represent opposite ends of cosmic time, both are pivotal to our comprehension of space, time, and matter. The Big Bang theory is the prevailing cosmological model for the observable universe's origins and development from an extremely hot and dense state about 13.8 billion years ago. This theory is supported by several key pieces of evidence. First, the cosmic microwave background, CMB, discovered in 1965 by Arno Penzias and Robert Wilson, is the thermal radiation left over from the time when the universe was in a hot, dense state. It's considered strong evidence for the Big Bang. Secondly, Edwin Hubble's observations in the 1920s showed that galaxies are moving away from each other, leading to the conclusion that the universe is expanding. This implies that at some point in the past, everything was much closer or even in a single point, the Big Bang. Additionally, the theory explains the observed cosmic abundances of hydrogen, helium, and lithium, which were formed during the first few minutes after the Big Bang, in a process known as Big Bang nucleosynthesis. Moreover, cosmic inflation, a refinement of the Big Bang model, suggests there was a rapid expansion of space itself in the very early universe, explaining the large-scale uniformity of the cosmos. The Big Bang theory outlines several key phases, including the Planck epoch, Grand Unification epoch, Inflationary epoch, Quark epoch, Hadron epoch, Lepton and nuclear epochs, Photon epoch, matter domination, recombination, and structure formation. Each phase marks a significant transition in the universe's evolution. Interestingly, the Big Bang theory finds echoes in religious texts like the Quran. For instance, Surah Al-Anbiya 21:30 and Surah Ad-Dariyat 51:47 are often cited as references to an expanding universe and the creation from a single point, aligning with the Big Bang concept. Now let's turn our gaze to black holes, the enigmatic cosmic entities that represent the end of stellar life cycles. Black holes form from the gravitational collapse of massive stars, or potentially from the collapse of dense regions in the early universe, known as primordial black holes. These mysterious objects are defined by their event horizon, the boundary beyond which nothing can escape their gravity, and the singularity where matter is compressed to infinite density. Black holes are characterized by mass, electric charge, and angular momentum, but nothing else as per the no-hair theorem. Hawking radiation, a quantum effect, causes black holes to emit radiation and eventually evaporate over vast timescales. Observational evidence of black holes comes from their gravitational effects on nearby matter, X-ray emissions from accretion disks, and gravitational waves from black hole mergers. Supermassive black holes at the centers of galaxies play a crucial role in galaxy dynamics and evolution through their gravity and activity. Comparing black holes with the Big Bang reveals intriguing contrasts and connections. Both involve singularities where the laws of physics break down, but while the Big Bang singularity marks the beginning of space-time, black hole singularities exist within space-time. Both challenge our understanding of physics, particularly where general relativity meets quantum mechanics. Black holes represent regions where matter and energy are concentrated to extreme levels, while the Big Bang describes the initial distribution of matter and energy across space. In a philosophical sense, black holes are often seen as endpoints, whereas the Big Bang signifies the beginning of everything we observe. In summary, the Big Bang and black holes are cosmic extremes that push the boundaries of our comprehension. They remind us that the universe is a place of both beginnings and endings, creation and destruction, and that our journey to understand it is far from complete. Through a Quranic lens, both black holes and the Big Bang theory can be subjects of interpretation, reflection, and sometimes controversy. Here's how these scientific concepts might be viewed or connected to Quranic narratives. Black holes, creation and destruction, Surah Al-Waqiah 56:75-76. The reference to setting places of the stars might be interpreted as an analogy for black holes where stars end their life cycles. This aligns with the notion of creation and destruction being part of the cosmic cycle, a theme that resonates with the Islamic concept of the universe having a beginning and an end. The unseen and the known. Black holes, being invisible and only detectable through their effects, can be seen as a metaphor for the unseen aspects of the universe that Allah alone knows fully. Surah Al-Mulk 67:3 speaks of 7 heavens, which some interpret as layers or dimensions of existence, potentially including phenomena like black holes. End of time. The idea of an event horizon where time and space behave differently could be metaphorically linked to the Quranic descriptions of the Day of Judgment, where time will end or be judged differently, as suggested in Surah Al-Anbiya 21:104, speaking of folding the heavens like a scroll. Big Bang origin of the universe, Surah Al-Anbiya 21:30. The heavens and the earth were a joined entity, and we separated them. This verse is often cited as a Quranic parallel to the Big Bang, where the universe expanded from a single point. It suggests a divine act of separation or creation from a unified state. Expansion of the universe, Surah Ad-Dariyat 51:47. And the heaven we constructed with strength, and indeed we are its expander. This is interpreted by some as an early mention of the expanding universe, a key aspect of the Big Bang theory. Creation from smoke, Surah Fusilat 41:11. Then he directed himself to the heaven while it was smoke, and said to it and to the earth, "Come into being, willingly or by compulsion." The smoke can be likened to the pre-stellar gas clouds in the early universe or the hot, dense state before expansion. Connections and interpretations, divine knowledge versus human discovery. Both black holes and the Big Bang illustrate the idea that human understanding of the cosmos is limited, but the Quran, from this perspective, hints at truths later uncovered by science, showcasing divine omniscience, creation, order, and purpose. The Quran frequently emphasizes the order and purpose in creation. The Big Bang theory, showing how the universe evolved from chaos to structure, might resonate with Quranic narratives of Allah's meticulous design, as in Surah Al-Furqan 25:2, where it said, "He who created the heavens and the earth and what is between them in 6 days." Time and eternity. Both concepts challenge human perception of time. Black holes and how they affect time near their event horizons, and the Big Bang and how it sets the temporal framework of the universe. This can be paralleled with Quranic descriptions of time being different in the hereafter, as in Surah Al-Hajj 22:47. Cosmic scale and divine magnificence. The vast scales involved in black holes and the Big Bang amplify the awe of creation, reflecting the Quranic theme of Allah's grandeur, as articulated in verses like Surah Al-Baqarah 2:255, the throne verse, which speaks of Allah's dominion over the heavens and the earth. Caveats in interpretation, metaphorical language. Quranic verses are often poetic and metaphorical, not scientific treatises. Thus, interpretations linking the Quran to modern science must be cautious not to overstep the text's intent. Historical context. The Quran was revealed in an era with a very different understanding of cosmology, so any scientific parallels should be considered within this context. Diversity of opinion. Within Islamic scholarship, there's a range of views on how much one can correlate Quranic verses with scientific concepts, from those who see harmony to those advocating for a clear separation between faith and science. In essence, through a Quranic lens, black holes and the Big Bang can be seen as part of the divine tapestry of creation, destruction, and the cosmic cycle, inviting believers to reflect on the signs of Allah in the universe while acknowledging the limits of human knowledge. When examining black holes from a Quranic perspective, we encounter a fascinating intersection of ancient scripture and modern scientific discovery. Here's a summary of key points: divine signs and mysteries. Black holes, with their enigmatic nature, can be seen as part of the Quranic invitation to ponder upon the signs, ayat, of Allah in the universe. Their hidden yet influential presence in the cosmos might be paralleled with the Quran's mention of the unseen, al-ghaib, encouraging believers to reflect on what is beyond human perception. Creation and destruction. The life cycle of stars leading to black holes can resonate with Quranic themes of creation, transformation, and destruction, illustrating the transient nature of the physical world against the eternal divine plan. Passages about the heavens and earth being created from smoke or the setting places of stars can be metaphorically linked to stellar evolution and black hole formation. The nature of time and space. Black holes challenge our understanding of time and space, much like the Quran's depiction of time in the hereafter, where it is perceived differently. This can lead to theological reflections on the nature of reality, time, and the end of existence, aligning with Quranic verses about the Day of Judgment and the folding of the heavens. Philosophical inquiry. The concept of a black hole's event horizon, where escape is impossible, can evoke discussions on predestination versus free will, a significant theme in Islamic theology. It prompts contemplation on human destiny, divine will, and the limits of human knowledge. Science as worship. The study of black holes in this context becomes an act of worship, an exploration of Allah's creation. This aligns with the Islamic emphasis on seeking knowledge as a form of devotion, fostering a sense of awe and humility before the complexities of the universe. Integration and interpretation. While some might interpret certain verses as referring to black holes or similar cosmic phenomena, this must be done with caution. The metaphorical and poetic language of the Quran should not be overly literalized to fit modern science, but rather, the parallels can inspire deeper spiritual and philosophical reflection. Ethical and moral dimensions. The study of black holes also brings ethical considerations, particularly in how we approach the mysteries of the universe. It invites questions about our responsibility as stewards of knowledge, how we apply this knowledge, and the moral implications of exploring such profound cosmic entities. Cultural impact. The discourse around black holes in Islamic contexts can influence art, literature, and education, encouraging a narrative where science and faith are not in conflict but rather complement each other, enriching Muslim cultural expressions and educational systems. Ongoing dialogue. The exploration of black holes through a Quranic lens is part of an ongoing dialogue within Islamic thought about the relationship between science and religion. It serves as a testament to the dynamic nature of Islamic scholarship, which continues to engage with new scientific discoveries while maintaining its spiritual core. In conclusion, black holes, when viewed through a Quranic lens, offer a profound space for reflection, where the marvels of creation meet the mysteries of the divine. This perspective not only enriches the scientific understanding of the universe but also deepens the spiritual connection to the Creator, recognizing the limits of human knowledge while celebrating the pursuit of understanding as a path to faith. However, this exploration must be approached with an appreciation for both the scientific method and the sacred text's intended meanings, fostering a balanced dialogue between the empirical and the eternal. In the realm of the very small, where particles dance to the tune of quantum mechanics, black holes present a paradox that challenges our understanding of the universe. Hawking radiation. Stephen Hawking revolutionized our view of black holes by proposing that they are not entirely black. Instead, they can emit radiation, now known as Hawking radiation. This phenomenon suggests that black holes can slowly lose mass and eventually evaporate, with radiation intensity inversely related to their mass. This groundbreaking idea bridges the gap between quantum mechanics and general relativity, hinting at the elusive theory of quantum gravity. Primordial black holes. Imagine black holes that formed not from dying stars, but from the intense conditions of the early universe. These primordial black holes could have emerged due to density fluctuations shortly after the Big Bang. If detected, they could provide invaluable insights into the universe's infancy and the nature of dark matter. Philosophical and cosmological implications. The mysteries of black holes extend beyond physics, touching upon deep philosophical questions. The information paradox, for instance, asks what happens to the information contained in matter that falls into a black hole. This paradox is linked to the concept of black holes having no hair, meaning they are defined by only a few properties and seemingly erase detailed information about what falls into them. Another intriguing hypothesis is Roger Penrose's cosmic censorship conjecture, which suggests that singularities, the infinitely dense cores of black holes, should always be hidden by event horizons. This conjecture aims to prevent naked singularities from disrupting the observable universe, preserving the predictability of physical laws. Neutron stars. Beyond black holes, the universe presents other extreme objects like neutron stars. These remnants of stellar evolution form when a star with a mass between about 1.4 and 3 times that of the Sun exhausts its nuclear fuel and undergoes a supernova explosion. The core collapses to an immense density, where protons and electrons combine to form neutrons. Neutron stars are incredibly dense, with a teaspoon of their material weighing billions of tons on Earth. They possess some of the strongest magnetic fields in the universe and often rotate rapidly, with some spinning hundreds of times per second. Observationally, neutron stars can manifest as pulsars, emitting beams of radiation that sweep past Earth, creating a pulsating effect. In binary systems, they can accrete matter from a companion star, radiating X-rays. Specific examples. Consider PSR 1913 plus 16, a binary pulsar system where 2 neutron stars orbit each other. This system has been crucial in confirming predictions of general relativity, including the emission of gravitational waves. Theoretical implications. Studying neutron stars offers insights into nuclear physics under extreme conditions, unattainable in earthly laboratories. It also aids in understanding the upper mass limits before a star collapses into a black hole, as both share similar endpoints of stellar evolution but differ in mass and subsequent behavior. As we delve deeper into the quantum realm and the cosmos, black holes and neutron stars continue to challenge and expand our understanding, offering glimpses into the fundamental workings of the universe. Formation process. Stellar evolution. Neutron stars are the remnants of massive stars, those between approximately 8 and 20 times the mass of the Sun, after they've gone through their life cycles. When these stars exhaust their nuclear fuel, fusion no longer counteracts gravitational collapse, supernova explosion. The core of such a star collapses suddenly, leading to a supernova explosion, one of the most energetic events in the cosmos. This explosion ejects much of the star's outer layers into space while the core undergoes extreme compression. Core collapse. The core's collapse is halted by nuclear forces. Protons and electrons combine to form neutrons, and the density increases dramatically, leading to the creation of a neutron star. Equation of state. The behavior of matter at these densities is described by the neutron star's equation of state, which is still a subject of active research. This involves understanding how nuclear matter behaves under pressures billions of times those at Earth's core. Physical characteristics. Density. Neutron stars have densities where a sugar cube-sized amount of material would weigh around 1 billion tons. The matter inside is so dense it's thought to be in a state where even atoms no longer exist, and matter is described by quantum chromodynamics, QCD. Radius. Typically, a neutron star has a radius of about 10-20 kilometers, making them one of the smallest yet densest objects known in the universe. Magnetic fields. Their magnetic fields are extraordinarily strong, often measured in units of Tesla, where they can be on the order of 10 circumflex 8 to 10 circumflex 15 T. This is billions to trillions times stronger than Earth's magnetic field. These fields can shape the behavior of charged particles around the star, leading to various emission mechanisms. Rotation. Due to the conservation of angular momentum, when a large star contracts to form a neutron star, its rotation speed increases dramatically. Some neutron stars spin hundreds of times per second, making them excellent cosmic clocks. As we delve deeper into the cosmos, we encounter another fascinating phenomenon associated with neutron stars: pulsar wind nebulae. These are intricate, glowing regions of space created by the energetic winds emanating from a pulsar, the highly magnetized, rotating neutron star we discussed earlier. Formation and structure. When a pulsar emits its powerful wind, composed of charged particles, it interacts with the surrounding interstellar medium. This interaction generates shock waves, which in turn produce synchrotron radiation, lighting up the nebula in various wavelengths, including X-rays and radio waves, energetic jets and filaments. The pulsar wind can also create spectacular jets and filaments, structures that extend vast distances across space. These jets are often aligned with the pulsar's magnetic poles and can be incredibly dynamic, changing over time as the pulsar spins and emits its wind. Mysteries in research. Despite decades of study, pulsar wind nebulae still hold many secrets. Researchers are particularly interested in understanding how the wind particles are accelerated to such high energies and how the nebula's complex structures form and evolve. Advanced telescopes, both on Earth and in space, continue to provide new insights into these enigmatic celestial objects. Cosmic laboratories. Pulsar wind nebulae serve as natural laboratories for studying high-energy astrophysics, particle acceleration, and the behavior of matter and magnetic fields under extreme conditions. They are crucial for testing our theories of the universe and pushing the boundaries of our scientific knowledge. In essence, pulsar wind nebulae not only enhance our understanding of neutron stars but also offer a window into the dynamic and ever-changing nature of the cosmos. As we continue to explore these phenomena, we inch closer to unraveling the intricate tapestry of the universe. Join us in our next scene as we explore the interplay between black holes and neutron stars, uncovering the dramatic cosmic events they orchestrate. As we journey through the cosmic wonders of the universe, we find ourselves intrigued by the potential connections between ancient texts and modern scientific discoveries. In this scene, we delve into the Quranic verses that some interpret as references to phenomena akin to black holes. Quranic verses often cited. Several verses in the Quran are sometimes interpreted to refer to phenomena akin to black holes. Surah Al-Waqiah, 56:75-76. But nay, I swear by the setting places of the stars, and verily this is a mighty oath if you but knew. Some interpretations suggest that setting places of the stars could metaphorically or literally refer to black holes, where stars end their life cycle. Surah at-Tariq, January 3, 86. By the heaven and the Tariq, the knocker. And what will convey to you what the Tariq is, the piercing star. Here, Tariq or the knocker is interpreted by some to possibly describe a black hole where piercing could relate to the intense gravitational pull or the knocking effect of gravitational waves. Surah Al-Najm, 53:1. By the star when it sets. This is sometimes linked to the idea of a star collapsing into a black hole. Interpretations and claims, scientific miracles. Advocates of the Quran's scientific miracles argue that these verses indicate knowledge of black holes long before modern science understood them, suggesting divine revelation. Linguistic analysis. Terms like mawaki, places where stars fall, and thaqib, piercing from the Quran, are scrutinized for possible connections to black hole characteristics like gravitational collapse or light absorption. Cosmological events. Some interpretations extend to broader cosmological events, suggesting parallels between Quranic descriptions and modern astrophysical phenomena like quasars or the dynamics of galaxy formation. Conclusion. While there are fascinating connections between Quranic verses and modern scientific concepts like black holes, the interpretations are largely speculative and subject to debate. The Quran's language is rich in metaphor, and while it might resonate with modern scientific understanding, these parallels should be approached with caution, recognizing the difference between spiritual allegory and scientific fact. Join us in our next scene as we continue our exploration of the cosmos, bridging the realms of science and spirituality.